Hello friends, welcome to lecture series on essential mathematics for machine learning. So, in the last lecture we have seen some numerical optimization, some concepts of numerical optimization. We have seen a basic steepest descent method to solve an unconstrained optimization problem. In this method basically I have already discussed that we have take a direction that is which is negative of gradient of f, in which f decreases most rapidly, and we move from x k to x k plus 1 such that x k plus 1 is nothing but x k plus alpha k d k, where d k is the direction that is the negative gradient of f at x k, and alpha k is the optimal step size. In this lecture we will see some more techniques which is required in machine learning. So, first of all Newton's method. So, what Newton's method is? If we have an equation say y equal to f x or f x equal to 0, we want to solve this equation f x equal to 0, we want to find out the root of this equation. Then how can you find the root of this equation? That we have so many methods in numerical analysis. One of them is Newton-Raphson method, in which basically here we are having g y equal to 0. Okay. Now, we want to find the root of this equation for which y g y is equal to 0. So, how we can find out at least approximate root of this equation? So, that for that we have a recursive algorithm that is given as that this recursive algorithm is called Newton-Raphson method. So, what this method is basically, we go from one iteration to other iteration in such a way. First we fix a initial guess, say that initial guess is y 1 or y 0, you can take y 0. Then from y 0 to y 1, if you put k equal to 0, so that is equal to g y 0 upon g dash y 0. Okay. Of course, g dash y 0, g dash y k should not equal to 0 for any y k. This method will work only when g dash y k is not equal to 0 for any y k. So, as this y k plus 1 tends to y k, that means we are tending towards a solution. Now, if you are having in the same lines, if you are having an unconstrained optimization problem, which is minimization of f x subject to x belongs to R n without any restriction on n, x may be any vector in R n. So, how we can find, how we can optimize, how we can minimize this function f? So, for that suppose it is given to us as function f is differentiable, the differentiable function. Then of course, if you want to maximize if minimize this, that means we want to find out the root of this equation gradient of f x equal to 0, we want to find out that x bar where gradient equal to 0, because if you want to maximize or minimize a function, that means we have to do dy by dx for a single variable function. Here it is n variable function. So, if for a single variable function, how we can find out maximum or minima? We first find dy by dx, put it equal to 0, that will give critical points, and we find second derivatives, for we see that where it is maxima or minima or higher order derivatives. If it is n variable function, so what are those points where it attains minima, where gradient is equal to 0? So, that means instead of solving this problem, we have to solve this equation, we have to solve this actually system of equations, we have to find that x bar where this is equal to 0. So, how can we solve this equation, how we can find out that x bar where this is equal to 0? So, that can be found using Newton's scheme, and that Newton's scheme is basically, it is on the same lines as a Newton-Raphson method, that is x k plus 1 equal to x k minus Hessian matrix of x k at x k whole inverse into gradient of f x k. Now, how we arrive at this recursive formula, how we obtain this? So, the derivation is quite easy. So, let us see. Suppose you approximate this f x by the Taylor series as f x k plus x minus x k whole transpose gradient of f x k plus 1 by 2 x minus x k whole transpose Hessian matrix of f at x k into x minus x k. So, we take a quadratic approximation of this function by the Taylor series expansion. Now, what we want? We want that x where gradient of f x equal to 0. Okay, we want this. Now take the gradient of f respect to x both sides and let us see what we will obtain. So this implies, so this is equal to 0. Now this is x k, a fixed point. So if this is a fixed point, so gradient of this will be 0. Now this is x into this. So when you differentiate this with respect to partially differentiate with respect to x, so that is nothing but gradient of f x k. The second term is of course 0 because x k is fixed, and when you differentiate this respect to x partially, then we will get what, plus Hessian matrix of f at x k into x minus x k, and that must be 0. Okay. Now this implies Hessian matrix of f at x k into x minus x k is equal to minus of gradient of f x k. Okay. And this implies, suppose this is invertible. Okay. Now if this is invertible, so we can write x minus x k is equals to negative of h f x k whole inverse into gradient of f x k, and this implies x equal to x k minus h f x k, that means Hessian matrix of f at x k into gradient of f x k. So this is nothing but x k plus 1, the next iteration. So as soon as this approaches to this x k, we say that will be the optimal solution of a given problem. The limitation of this method is that we are supposing that Hessian matrix of f at x k is invertible for every x k. If it is not, then this method is not applicable. Okay. So h f x k is a invertible matrix at x equal to x k. So this is our supposition. So basically this I have already explained you. Now this method has the order of convergence 2, that is p is equal to 2 for this method, and it has a descent property that we can easily show. Descent property means f at x k plus 1 is less than f at x k. For solving quadratic functions involving positive definite quadratic form, it will take exactly one iteration to find out the optimal solution, exactly one step. So let us see one problem based on this. Suppose this is a quadratic expression which you want to minimize. It is an unconstrained optimization problem, and suppose the initial guess is 1 2. You can take other initial guess also. I am taken initial guess as 1 2. So how we can find out the optimal solution of this problem using Newton's method. So what is the problem we are having? So minimization of f x 1 x 2, which is equal to x 1 square minus 3 x 1 x 2 plus x 2 square. 3 x 2 square, oh sorry, it is 3 x 2 square, and initial guess is 1 2 transpose. So this is the initial guess we are having. So first you find gradient of f. Gradient of f be del f upon del x 1, del f upon del x 2. That will be 2 x 1 minus x 2 and minus x 1 plus 6 x 2. This transpose will be the gradient of f. Okay. Now what is Hessian matrix of f? This is 2 minus 1 6. Okay. Now this is always invertible. This is 12. This is determinant of HF is always non-zero. So for any x k, because it is independent of x. Okay. If you want x2 means x1 minus Hessian matrix of f at x1 whole inverse gradient of f at x1. This is by Newton's method, Newton's formula. So what is gradient of f at x1? Now gradient of f at x1 is this is x1 basically, x1 is 1 2. Now you substitute 1 and 2, so it is 0. You substitute 1 here, 2 here, so it is 11. Okay. So now x1 is 1 2 minus Hessian matrix is, now you have to find the inverse of this matrix. So what is the inverse of this matrix? inverse of this matrix will be 6 2, and this is again I think -1 or 1 1. So, it is 1 1, it is 1 1, and that is divided by the determinant of this, which is 1 upon 11, determinant is 11 here, into gradient of f at x 1, that is 0 11. So, this is 1 2 minus, it is 6 1 1 2, and that will be 0 1. So, this is 1 2 minus this row, this column is 1, this row, this column is 2, and that is simply 0 0. So, x 2 comes out to be 0 0. Now, if you find x 3, so what will be x 3? X 3 will be x 2 minus Hessian matrix of x 2 whole inverse gradient of f x 2. So, x 2 is 0 0, this is same, which is 6 2 1 1, and what is gradient of f x 2 at 0 0? At 0 0 it is obviously 0. So, when gradient of f at x 2 comes out to be 0, that means it is an point of minima. So, of course, that will be a point of minima, that which we can verify from here also. So, this is 0 0. So, that means 0 0 is the point of minima, is a point of minima. Okay. So, since this is positive definite form, so this method converges only in one iteration. So, this is Newton's method for solving such type of problems. Now how can we solve a constraint optimization model? So, here I am discussing one method, that is penalty method, that how we can discuss a constraint optimization problem. Now, suppose you are having a nonlinear programming problem like this, that is minimization of f x subject to g I x less than equal to 0 I from 1 to m, and suppose this f and all g i's are differentiable functions. So, a numerical optimization technique for constraint optimization problem aims at converting the NLP to an unconstrained optimization problem, which can be solved using numerical technique for unconstrained optimization problem. If you are having any constraint optimization problem, the main aim of any algorithm for handling constraint optimization problem is to convert that problem into unconstrained type. If we can convert that problem into unconstrained type, then the usual technique like descent method or other methods we can apply for solving that problem. So, one such method is penalty function method. Now, what is a penalty function? In penalty function, what we do? We define a function p x, p tilde x, which we say that it is 0 if x belongs to S. Here S is a feasible region. Okay. So, S is a feasible region which is consisting of all x such that g I x less than equal to 0 for all I, and we are saying that it is infinity if x does not belongs to S, belongs to x. So, of course, if we minimize this function, that means if x belongs to S, then this will be 0. If x belongs to S, that means x is a feasible region, x is a feasible point, and then this will be 0. Then minimum of this function and minimum of this function will coincide. That means the NLP, the problem NLP and this modified unconstrained optimization problems are equivalent. And if x does not belongs to S, then this will tends to infinity. Okay. So, the main aim is this will be a minimum if this belongs to, if this is 0, and that is possible when x is in feasible region. That means we are finding a feasible point where we are minimizing simultaneously f x. So, this unconstrained optimization model is basically equivalent to the problem NLP. Now, the problem here is that this function is not smooth, not differentiable, it is discontinuous. Okay. So, if we have converted this problem into an unconstrained optimization model, and if we want to apply the techniques for the numerical techniques for solving unconstrained optimization model, then those methods may not be applicable. So, how we can make this problem as a smooth problem, I mean differentiable problem, so that the techniques of unconstrained optimization problem may work. So, what we do, we define a function p x, the penalty function p x, as maximum of g I x and 0, this whole square and sum up to I from 1 to m. Of course, again if we are minimizing f x plus alpha times p x, see if x is in S, S means feasible region. If x is in feasible region, that means g I x is less than equal to 0 for all I. If g I x is less than equal to 0 for all I, then the maximum of g I x and 0 will be nothing but 0 itself, and the sum of squares of 0 is 0. So, that means this will be 0, that means it will comes to minimum of f x. The same problem, that means feasible x such that minimum of f x, that means finding the optimal solution of this unconstrained optimization model is same as finding an optimal solution of the constraint optimization problem NLP. Why we have constructed a penalty function like this? We can construct, there are other methods also to find the penalty function, this is one of them, to make the function smooth. Okay. Here we attach alpha also. Alpha is a sequence basically. You can take alpha as 1, alpha as 10, alpha as 100. We increase alpha, we tend it to infinity basically. We tend into infinity, so that f x will approach to that, so that this function will approach to f x. So, this is the main algorithm basically. What is the algorithm? First of all, we define a suitable penalty function. Here we have taken penalty function as sum of maximum of g I x and 0 whole square. Then choose an increasing sequence of positive real numbers which tends to infinity, that is sequence alpha k from 1 to infinity, such that alpha k is greater than 0 and alpha k plus 1 is greater than alpha k. In general, we take alpha 1 as first 1, alpha 2 as 10, alpha 3 as 100, alpha 4 as 1000, so on. Then we choose the arbitrary starting point x naught in Rn and construct the following unconstrained minimization problem as this, okay, and solve it using unconstrained minimization technique. You can use steepest descent method or you can use some other technique for solving this unconstrained optimization model. Now, if x1 is the optimal solution of this for alpha 1, then taking that x1 as an initial guess, put here alpha 2 and find again the optimal solution of that unconstrained optimization model using any unconstrained minimization technique. The process will go on till we have either alpha k p k p x k less than epsilon, that means this is very small, penalty function is very small, or this q x alpha k minus f x k is very small, which is one and the same thing basically for some tolerance level alpha epsilon greater than 0. So, this is the main idea behind this, this is the main algorithm behind penalty function method. How we can say that this is convergent? So, we have various theorems also, we are not going to discuss the proof of the theorems, I am just stating here for your understanding. So, what is the first lemma or the theorem is, let alpha bar, let x k bar denote the optimal solution of UMP at alpha equal to alpha k. UMP is unconstrained minimization problem, this is this problem, okay, that is this equal to this, that is this minimum is attained at x equal to x bar, x k bar, where q x alpha k is this, alpha k greater than 0. Then the first of all at x k plus 1 whatever we have obtained and at alpha k plus 1, this is always greater than or equal to this term, that means this quantities keep on increasing. Now, p k x k bar is greater than or equal to p k x k plus 1 and f k is always less than or equal to f k plus 1, that means this we are going to minimize. Now, the second lemma is, if let x bar be an optimal solution of a given nonlinear programming problem NLP, then for each k this inequality holds, that means we are always that means at x k plus 1 it is always less than or equal to f x bar, where x bar is an optimal solution. So, let us discuss this example quickly by this problem. We have to solve the NLP using penalty function method starting with x naught equal to 2 2 and epsilon equal to 0.001. So, let us see what is the problem. The problem here is we have to minimize 3 x 1 square plus 2 x 2 square plus 2 x 1 x 2 minus 20 x 1 minus 16 x 2 subject to x 1 plus x 2 equal to 5. Now, how we can use penalty function here? X 1 plus x 2 equal to 5 can be written as x 1 plus x 2 less than equal to 5 and x 1 plus x 2 greater than equal to 5. This can be written as minus x 1 minus x 2 less than equal to minus 5 or minus x 1 minus x 2 plus 5 less than equal to 0, and this is basically x 1 plus x 2 minus 5 less than equal to 0. So, how can we define penalty function now? So, penalty function will be defined in here as maximum of x 1 plus x 2 minus 5, the first constraint 0 whole square plus the second constraint maximum of the second constraint 0 and whole square. That is a penalty function. Now, if this is negative, if this is, suppose this is negative, then maximum will be 0 from here, and then this will be positive, then this is the maximum, and if this is negative, then maximum is 0 here and this is positive. In either case, in any case, we are having this as a penalty function. Okay, because if this is negative, then we will get 0 here, but on the same, if this is negative, then this will be positive, then the maximum of these two will be this only, this square, and if this is negative, then from here it is 0 and from here it is x 1 plus x 2 minus 5. So, in any case we will get the penalty function as x 1 plus x 2 minus 5 whole square. So, what will be our unconstrained problem now? Minimization of f x plus alpha k into x 1 plus x 2 minus 5 whole square. This will be the unconstrained minimization problem which we are having now. Now, let us put alpha k equal to like k equal to 1. If we put k equal to 1 in this, take alpha 1 equal to 1 suppose. So, what will be this function? This is say this is g x. So, this is f x plus alpha 1 times x 1 plus x 2 minus 5 whole square. So, what is f x? F x is given to us as 3 x 1 square plus 2 x 2 square plus 2 x 1 x 2 minus 20 x 1 minus 16 x 2. Alpha 1 is 1 into x 1 square plus x 2 square plus 25 minus 10 x 1 minus 10 x 2 plus it is minus 10 x 1 minus 10 x 2 plus 2 x 1 x 2. So, this is nothing but 4 x 1 square plus 3 x 2 square plus 4 x 1 x 2 minus 30 x 1 minus 26 x 2 plus 25. Now, we have to minimize this, we have to minimize this g x. How we can minimize this g x? So, here it is a quadratic form, we can directly differentiate it also, or we can apply some numerical optimization technique for unconstrained minimization problem. So, we can use steepest descent method also to find optimal solution of this problem. So, how we can do that? We can take the initial guess as what given to us. Initial guess is 2 2 is given to us. So, it is x naught which is 2 2 is given to us. So, we find gradient of f is 8 x 1 plus 4 x 2 minus 30, and here it is 6 x 2 plus 4 x 1 minus 26. Okay. And then we find gradient of f at okay, here it is g, so it will be gradient of g. So, gradient of g at we have to find at 2 comma 2. So, that we can find out as 16 plus 8 minus 30, and it is 12 plus 8 minus 26, and that will be 24, that is minus 12, and that is 20 minus 6. So, that will be gradient of G. Okay. So, we know the method. A method is x 1 equal to x naught plus alpha naught and to minus of gradient of this, that is 12 and 6. Okay. So, here it is 30. So, it will be 30 itself. So, it is 30. So, it is 24 minus 30 is minus 6. So, it is minus 6. So, here it comes out to be 6. So, this is now this is 2 plus 6 alpha naught and again 2 plus 6 alpha naught. Okay. So, now as we do in steepest descent method, we will put this x 1 and this x 2 in this function g, and we will find out that alpha naught where this attains minima by putting derivative of g with respect to alpha naught equal to 0, and the process continue till you get an optimal solution of this problem. So, what I want to say that basically for once you get a penalty function, you define your gx, which is unconstrained optimization model like this, and changing the value of alpha 1. Here I have taken alpha 1 equal to 1 and solve it by steepest descent method. In the same way, you will put alpha 1 equal to 10, alpha 2 equal to 10, alpha 3 equal to 100, and so on till you get the required tolerance level. Okay. So, here when you put alpha k equal to 1 in this problem, then applying any unconstrained algorithm, unconstrained minimization algorithm, alpha 1 comes out to be this. This is basically optimal solution of this problem. Okay, optimal solution of this problem, and for this f x k comes out to be this. Q x k alpha k means it is g basically, g comes out to be this, p x k is this, and alpha k p x k is this, because alpha k is 1 here. If it is 1, then this is simply same. Okay. Now, take alpha k equal to 10, alpha 2 equal to 10. If alpha 2 equal to 10, apply the same algorithm, find out the optimal solution, same iteration, we will get this row. And for alpha k equal to 3, alpha will be 100, the optimal solutions comes out to be this. Now, here this is 0.0009, which is less than 0.001 as given in this problem as a stopping criteria. So, we will stop here. So, this is basically a method for solving constraint optimization model. So, basically in any constraint minimization algorithm, the main aim is to convert that problem into an unconstrained minimization problem, and then we will solve that unconstrained minimization problem by using any search technique. So, this is the main motive behind this. So, this is one illustration of one method. Similarly, we have so many other methods also for solving constraint minimization problems. So, we have seen that if we are having unconstrained minimization problem, we have various methods, steepest descent method, Newton's method, conjugate gradient method, other method also. And for solving constraint optimization problem also, we have various methods in the literature. One of them is penalty function method. So, using these techniques, using these numerical search techniques, we can develop our algorithm if we are having an optimization models in machine learning algorithms, and that we can solve either by unconstrained optimization methods or by constraint optimization methods. So, thank you.